Hello and welcome. So this is going to be the third lecture of the course. I understand it has been a difficult start, a baptism by fire if you wish, but we shall take things a little slower and we shall start building up slowly towards what we said at the beginning in the first two lectures. We will, the symmetries that we would, as I was saying at the beginning of the lectures, the symmetries that we would be interested in when we are looking at nature and fundamental laws, fundamental forces are continuous symmetries. But before we go to that, we'd start off with something a little simpler. We'll start off with discrete symmetries. Symmetries, of course, can be both discrete and continuous, but discrete symmetries are easier to describe. So we will start off with that. And let's start off and let's sort of figure out what's going on. So, as I say here, we will be looking at finite groups to begin with. And okay, so let's look at an example. Okay, so let's look at an example first up. As you can see that I've written down here, one of the very simplest things is sort of reflection, if you wish, or parity. That sort of takes, you take something, put a mirror, there's a reflection. And if you do this twice, you get back to the same thing. So x goes to minus x, and I do it once again, it sort of comes back to itself. So one of the things that you can think about is sort of an isosceles triangle, and you can. So then, what is going to happen is that you would look at the reflection about its vertical axis. And once you do that, you will see that this goes. So there is one flip, and that this is lifted invariant under a reflection about this vertical axis. That's in a sense symmetry. I write here that the second simplest symmetry operation is a rotation. If you're in 2 dimensions, it's performed about a point, but if you're in 3 dimensions, it's performed about an axis. Here we are speaking about reflection, rotations which are finite by looking at finite angles. Okay, so for example, hopefully this is charged now. So if you're looking at something like a square, okay, let me try and draw this. If you're looking at a square, so if you are looking at some axis, say like this, that's a bad one. So this is going to be left invariant under rotations of 90 degrees, right? So if you rotate this whole thing by sort of 90 degrees here, then the thing remains the same. So that's a simple example. And so as I write here, the square is left invariant by an anti-clockwise rotation about its center by 90 degrees. The inverse operation is a clockwise rotation. These 4 rotations generate the identity element. You can think about anti-clockwise rotations by angles of 2 pi over n, and this will generate what is called the cyclic group Zn, where n is an integer. Okay. Now, before we go on to giving you explicit examples, let's put down a few of the notions of group axioms, which are familiar to quite a few of you, I guess. But let's try to do this nonetheless. Okay. So what is a group? A group is a collection of these, operators, a1, a2, dot dot to, ak, and so on. And there is an operation that I defined as star here, and it has the following properties. So the following properties, which are important, which are very important, they define the group. The first one is closure. So that's the first one. So if you have any ordered pair of elements ai and aj, there exists a unique element, ak, which is related by the star operation. So ai and aj go to ak, and this happens for any ij and k. So you take two of these group elements, you sort of you have this operation of star between them. It necessarily has to produce an element which is again belonging to the same group. This is closure. Okay, so everything's in the group. Okay, so there is associativity. So there is it would not matter which way you are doing the operations. You can look at a star, ai star aj first, and then ak. This is going to be the same as ai with aj star ak first. So that is going to be the same. There's going to be something called a unique. So there's going to be a unit element. So every set G is going to contain a unique element E, such that E with any member AI, star with any member AI, equivalently is AI starred with E. Then this gives you back AI. Okay, so this is what is called the identity element or the unit element. And it also follows that E star E is also going to be equal to E. Now there has to be the existence of an inverse. So what is this? So this means that corresponding to every element AI, there would exist a unique element in G such that, which is its inverse, such that AI star AI inverse, again, is AI inverse star AI, and this gives you back the identity element. Okay. Now, when G contains a finite number of elements A1, A2, dot dot up to AN, this is a finite group, and N is called the order of the group. Of course, there could be infinite groups as well, when you have these all the way to infinity. One of the examples of an infinite group is the real numbers including 0. So this is an infinite group under addition, where you have replaced the star operation with plus, and this. So what is going to happen is elements are 0, positive real numbers, and negative real numbers. So it's clear that if x and y are real, then x plus y is also real. And each element x has an inverse element minus x, so that x plus minus x gives you 0. And it's very clear that 0 here plays the role of the identity. Okay. All right. Their real numbers also form a group under multiplication. In this case, you have to exclude 0. And the inverse of x is 1 over x, and the unit element in this case is 1. Okay. Very good. So let's look at a few examples of finite groups of lower order. So let's look at it, group of order 2 first. Okay. So this is a unique group which is called Z2, and with 2 elements. One element is the identity, and the second element is A, which is its own inverse. So now we're going to draw some multiplication tables for these finite groups, which are going to be very useful. Okay. So here is the element is the multiplication table for Z2. You order the elements here and the others here. So E with E gives you E. E with A gives you A, which is clear. Now, A with E gives you A again. And as it has to be, that A with A has to close into something of the group itself. The only remaining thing is E, and it has to go to E. Okay. So A has to be its own inverse. So that's what it is. So this A can be, I mean, reflections that we were saying at first, parity, 180-degree rotations, etc. Now let's look again. Now let's do a bit more. Let's think about a group of order 3. This is again going to be unique. One element is going to be the identity, and let A1 be the second element. Okay. So A1 cross A1 has to be the third element. Otherwise, A1 cross A1 becomes E, and this leads to A1, A1 being equal to E. And it would just, or the second possibility is that A1 cross A1 equal to E closes the group with only two elements. Okay, so we must have things such that A1 cross A1 is equal to A2. Otherwise, it just goes on to the thing that we described earlier. Okay. So this is Z3, so the cyclic group of order 3. So so this is something that we have to do. So E with all of these things will this is obviously fixed. Now A1 cross E is A1, A1 cross A1 is A2, A1 cross A2 has to be equal to E. That's the only way this is going to close. And now so what is going to happen is this is what is the the group table that you're going to draw here. So this is your group table. So what you have is A1 cross A1 equal to A2, and this is the cyclic group of order 3. And so at the end of the day, what you find is so A1 cross A2 is equal to E. So A2 is again A1 cross A1. So it just means that A1 cross A1 cross A1 is E. Okay. So this means that this is an element of order 3 and represents a rotation. Now it has to be a third. So it's a 120-degree rotation. So 360 makes it the whole thing. So 3 of these will go into a 360 rotation. So divided by 3, so it's 120 degrees. So this particular group represents a 120-degree rotation. Very good. This can be naturally generalized to any arbitrary n. Zn is going to be called the cyclic group of order n. And this is generated by this repeated action of one element, A to order n. So Zn is E, then A star A, then A star A, and so on. And so A to the n will be equal to E. Okay, so that's the idea. All right, so moving on, let's discuss groups of order 4. Okay, there are two possibilities here. First is obviously Z4, which we just discussed, and an interesting realization of Z4 is Z prime. This guy Z prime is equal to IZ. So it's very clear what's happening. So you have Z. So let's actually make this a little thinner. Z, then you have IZ, then you have minus Z, and then you have minus IZ, and then it just goes back onto Z, right? So that's a fun group. That's a fun way of trying to realize this. Okay. Where obviously Z is a complex number, and A here is going to be an element of order 4. The second group is interesting. It's called the dihedral group D2, and it has the following multiplication table. Um, yeah, so this is what is the dihedral group. We'll have a little more to say about this later, but yeah. So let's define something here, before we go ahead. So there is something. So the notion of an abelian group. So the notion of an abelian group is one for which two elements, I mean, commute with one another. So AI stroke AJ, star AJ is AJ star AI. If this is the case, then this is going to be called an abelian group. Otherwise, this group is going to be called a non-abelian group, right? Um, D2, as we see it, is this is still an abelian group. One way to notice that is to take this and draw this line through the center and see if you if you were to think of this as a matrix, just see whether it's symmetric or not. So you see it is. So A1, A1, A2, A2, A3, 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 A2, A2, A1, A1. So that's fine. So that's what we have. So that's good. Okay. So that's AD2 is an abelian group. Okay. Now D2 actually is the first of a family of infinite groups, which are called dihedral groups of order n, and they have a simple, simple interpretation in terms of mapping a plane polygon of n vertices onto itself. Okay, so this is this n equal to 2 corresponds to the invariance of invariance group of a line, and yeah, so that's that. So yeah, you can read more about this. There are other sorts of realizations as well. You could try and find, yeah, you could try and see this, and you could try and see these guys. So these are 2 x 2 matrices, and you can call them A1, A2, A3, A4, and see how they close. A1 is obviously equal to E. This is E, so this is A1, this is A2, and A3. You can do the, do the multiplication and see what you get. All right, so again, you can try to look at the functions of this sort, and you would also be able to see that these actually close on to the onto D2. Okay. All right. So okay. Let's see how far I want to do here. So there's okay. Let's sort of try and end this lecture with the notion of subgroups. So the notion of subgroups is that there is going to be in what we are trying to do here. So we'll have this notion of subgroups. So the subgroups, a subset of the elements of the entire group will also close to form a group itself. In this case, what you can look at you can look at and see is in Z2, in Z4, there is going to be a notion, for example, of something which is a subgroup, which is a Z2. So remember that what we had in Z4 was this, right? So Z4 was A squared A cube, right? That's what this was. So you can have a subgroup which is E and A squared, and that is going to form that this particular thing forms a subgroup, right? So we know that a to the 4 is equal to 1, is equal to E. So it's clear that if you take just E and A squared, then a squared would circle back. So that is going to be a subgroup. Okay. So that's again reasonably straightforward. And ultimately, it's more interesting to find out what the subgroups of the dihedral group are. So now there are actually three subgroups, three Z2 subgroups. These are generated by E and AI. I mean E and A1, E and A2, and also E and A3. Okay. Uh, what happens is, since you have A1 star A2 equal to A2 star A1, the elements of the first two subgroups commute with each other, and what we can do is we can express D2 as a direct product of these two commuting subgroups. So D can be expressed as Z2 cross Z2. Okay, and so let's sort of end with trying to understand what direct product means. So a direct product, let G and K be two groups, and these have elements GA and KI. A runs from A1 to NG, and I runs from 1 to NK. We can assemble now new elements. These will be the duplex of GA and KI. The rule being that when you are multiplying GK KI with GB KJ, then what you will be doing, what you'll get is, at the end of the day, GA star GB and KI star KJ. I mean, obviously, GA star GB will be in G, and KI star KJ will be in K. So you would be able to check. Straightforwardly, they are going to satisfy the group axioms, and they'll form a group which has order in G into NK. This is going to be called the direct product group of G cross K. And we need to remember that since G and K operate in different spaces, they will be taken as commuting subgroups, and the elements of the direct product can be written as GK KJ. So this, in a way, provides a simple. Provides a simple way to produce new groups of higher order. You can take two groups, one of order 2 and one of order 3, make thing of order 6, and so on, right? So that's what you can do. Okay, so I think, oops, sorry. So I think all we had to do is, okay, so I've been saying that I'm going to stop, but let's do one final little bit, and then we can stop for the day. We're going to state what is called the Lagranges theorem. Okay, the Lagranges theorem is something that addresses the existence of subgroups. Now, consider G with elements GA, where A goes from 1 to N. And suppose that this contains in it a subgroup H with n elements, such that Hi to Hn, such that this small n is actually less than big N. Of course, that is G. H is a subset of G. Okay. Now let's pick an element in G that is not in H. So the n elements of the form G1 cross Hi are elements of G, but not of H. Okay. Now, if something so if one of them were in H, we would have that so G1 star Hi would be equal to Hj, and G1 would be AJ star HI inverse, which is an element of H, contradicting our sort of initial hypothesis. So we have in this case a theorem which addresses, if you wish, the condition of existence of subgroups. Okay, so yes, so that's again, just to clarify this. So you could have some you could have a group, and that may or may not have any subgroups in it. And Lagrange's theorem is something that is going to that gives you an idea of how to go about uh, looking at whether or not there are existence of subgroups. And we'll try and elaborate this a little more. Yeah, I think this last little bit was a little rushed. But the idea, for this lecture, in a sense, was the fact that what we would do is we start off with finite groups, and where you are looking at a group with finite number of elements. What we started off first by saying is there are these certain group axioms which have to be followed. So there's closure, there's associativity, there's every group has to have a unit element. There also has to be for every group there also has to be an inverse element. And then we went on to looking at some finite groups of lower order. I gave you the we spoke about Z2, which was a group of order 2. We spoke about Z3. And when we moved on to groups of order 4, we saw that there were interesting possibilities out there. We spoke about Z4, which is something which is a cyclic group of order 4, which is a particular example of the Zn, which is a cyclic group of order n. But we then spoke of another group, which was called the dihedral group of D2, and that had that had something some other multiplication table. I also told you about something we will see going ahead, something which is called an abelian group versus a non-abelian group. An abelian group is where AI star AJ is equal to AJ star AI. D2 is an abelian group. We will see some examples of non-abelian groups going forward. And then I gave you some more ways of trying to realize D2, and these this 2x2 matrices were one, these functions were another. And at the end of the day, I spoke to you a little bit about the notion of subgroups, and whereby groups of order 4 have this notion of subgroups. And I showed you for Z4 we have a natural Z2, which is generated by E and A squared. D2 also has three interesting Z2 subgroups, which are generated by EAI, EA2, and EA3. And we saw that what we can do is actually, since A1 star A2 is A2 star A1, the elements of the first two subgroups commute with each other, and we can express D2 as this direct product over these two commuting subgroups, and D2 can be expressed as Z2 cross Z2. And finally, I showed you a little bit about how exactly you did. You formalize this direct product definition, where you have two groups G and K, and you construct something with them by looking at elements GA, KI. And you can see that with this rule that I have outlined here, you would be able to show that these satisfy group axioms, and this is called the product group of G cross K. The last thing was a little fast, so let's actually get back to that in the next lecture. And so that's it for this lecture, which I guess was a little long, but that's all for the moment. So thank you guys, and I will see you guys soon in the next lecture sometime.